This is a recording from the University of Virginia and the More Than the Score lecture series, made possible by the university's Office of Engagement. The finite availability of fossil fuels has prompted a hunt for alternative resources to power us into the future. On September 12, 2009, chemical engineering professor Robert Davis discussed some of the current ideas and challenges related to the use of renewable biomass as a replacement for oil, coal, and natural gas.
I'm really excited to introduce Robert J. Davis talking about what he calls transforming the fossil era. Bob is got his PhD in chemical engineering from Stanford in 1989. He worked on postdoc in the chemistry department at the University of Namur in Belgium. He joined the faculty of chemical engineering at the University of Virginia in 1990. As an assistant professor, and currently holds the Ernest Jackson Oglesby Professor, which he received in 2009. He also, as Althea said, is department chair and has been doing that since 2002. His knowledge and information about alternative opportunities in the future to current fossil fuels is phenomenal. He has received the Emmett Award for the North American Catalysis Society, the NSF Young Investigator Award, DuPont Young Professor Award, Union Carbide Innovation Recognition Award, and the UVA Rodman Scholar Award for Excellence in Teaching. So you are dealing with someone who is just an exceptional person. He does have a textbook entitled The Fundamentals of Chemical Reaction Engineering. So let's welcome him here today, and I think you're going to be really excited by what he has to say. Thank you. Bob?
Well, it is a pleasure to be here. This is pretty amazing for me. I've never been involved with this series before, and I've never taught a Saturday class. And I've always thought that if I did teach a class, I would never have anyone show up. But this is actually amazing. So I want to talk to you a little bit about what I do when I'm not in the classroom. My research program is probably 80% dedicated to looking at renewables. When I mean renewables, looking at biomass to fuels and chemicals. So if you're thinking about solar energy or wind, that's really what I'm not going to address today. I'm really going to be talking about biomass. Now, what I want to do is talk about why this is a problem we should be thinking about, so kind of an introductory part, and then what is out there in the newspapers. What are you seeing, and what are the real technology options that are being discussed, and what are the problems with them? And so I don't have the answers. I just want to kind of educate you as to what the problems are and where the field is going. So to start off this lecture, I thought I would lay out what Richard Smalley, who was a Nobel Prize winner in chemistry, he invented the buckyballs, you may have heard, Buckminster fullerene, and he passed away a few years ago, but he dedicated the last few years of his life to really educating the government and the whole country in the energy problem. And he's written many papers in this area and delivered many lectures. And I saw one of his lectures. It was just astounding. But he put up his view of the top 10 problems facing humanity. And if you read his papers about it, he says, well, you know, I put energy as number one because if you think about it, if we have clean water, and we can come up with clean water, we can desalinate water, ocean water, but it takes energy to do that. But if we have clean water, we can grow enough food. And if we have enough food, we can feed large populations. So many of the problems lower on this list can be solved if we have abundant, cheap sources of energy. And so he really puts energy as the number one problem facing humanity in the near future. And so that's why it's something we really should concern ourselves about. If we look at the projections for world population, we're pretty good at this. Okay, you see this line shown on this graph, and I apologize to those listening to podcast. As an engineer, I have to have lots of graphs and slides, so I'll be referring most of the time to the graphs on the screen. But you can see the world population right now is almost 7 billion people. In the U.S., it's over 300, and that's just from September 2nd. And the projections are right on target. I mean, we were pretty good at predicting this. So it's going to be near 10 billion people pretty soon. And people are what consumes energy, right? And you can see here, this is a very famous picture of the world at night. And what you see is where essentially energy use occurs. And you can see the United States on the East Coast particularly, very well lit up, Western Europe and Japan. But the economies of India and China are rapidly growing, and the number of people there and their desire to reach our standard of living is going to place a tremendous demand on the world energy use. All right, so how do we use energy in the United States? As you see here, fossil energy is the vast majority, 85.6. I borrowed this slide from a colleague of mine in my department. About 10% nuclear and very little renewable energy. And as you can see, what that renewable energy is composed of: hydroelectric, some biomass, and a lot of the biomass previously was, left over from paper plants that you could go and burn for fuel and energy. And now we have these ethanol mandates in this country, and so that's increasing the use of renewables. But it's still very, very small. And then there are very trivial amounts of geothermal and wind and solar. But as you can see, the fossil use, which is 86%, a large portion is oil, and then there's coal and natural gas as the other two. So it's a lot. You can see 84 million barrels per day of oil used globally, 21 of those in the United States. So these are huge, huge numbers. And so the problem with energy is it's a game of scale, and the scales are mind-boggling. So if we look back in how we used energy in the past, really, this is what I call ancient energy, that's why it's in quotes. It really was biomass, right? It was burning charcoals, agricultural waste, trees, animal dung, so on. So it really was biomass. And these are obviously not very efficient ways to go, but still 2 billion people today use this form of energy in the world. Okay, but as standards of living are going to increase, this is going to change. In the 1800s, coal really came into its own. It spurred the Industrial Revolution, and at that time, nobody ever thought we would have any need or find anything else other than coal. And, of course, there was little bits of oil that were found and talked about, but it was really not a major player. But when the internal combustion engine came along, that's really what revolutionized our use of oil. And that's the 1900s, and you can see here why Texas and Houston became the world's energy capital at that time. And so we've lived a century really dependent on oil, okay? And our domestic supply of oil ramped up very rapidly. So this is a plot showing proved reserves from 1900 all the way to projected to about 2006. And what you see is we're now in the decline for proven reserves in this country. And the question is, what's going on in the rest of the world? And you talk to various energy agencies, and those plots shift and the projections shift. But people still say we are near the peak, or we're 50 years away from the peak, but we're going to reach a peak. Okay, that's the age of easy oil is over. We're finding more oil. You know, you read in the newspapers drilling in the Gulf, and you can go down many miles and find oil, but it's getting harder and harder to get it. Okay, so it's out there still, and we're finding it, but it's not easy anymore. And you can see at least in the U.S., the reserves are declining. All right, where is the oil today? As you might expect, it's in the Middle East. You know, large amounts of it in the Middle East. Okay, so oil supplies are in question, and they're not where we want them to be. Okay, and the costs. This is what everybody talks about, right? What happened? And so what I've taken here is I've plotted the real price and the nominal price. So the real price is essentially it's adjusted for the current consumer price index. And you can see it reached over 120, almost $130 per barrel in 2008. And the only bright side of the recession, is that the price of energy dropped. So one has to realize that energy depends on the number of people wanting it and the economic activity. All right, so obviously the people haven't changed. It's just that the recession caused a decrease in economic activity. So as we raise standard of living and grow the population, the energy requirements are going to go way up. So the recession just shows you that when economic activity drops, demand drops. Let's talk about coal. Where is the coal? Well, coal, there's a lot of coal here. North America, Europe, and Eurasia, and Asia Pacific, you can see, are almost evenly distributed on this plot from BP's statistical review in 2006. If we look at it by country, you can see the U.S. actually leads. You can see Russia next to it. Let's see, do I have a pointer here? Yeah. So here's the U.S. in blue, and then here's Russia, and then China and India as we go around here. and then all the rest of the world in this orange. So there's a lot of coal in the United States. And so this is one resource that has been discussed at length about using coal as an alternative energy source to the questionable acquisition of oil. Okay, but you have to process coal. So that's a different issue. When we use coal, there's going to be a lot of CO2 generation, and extraction costs are non-trivial. It's not like oil. Oil is nice because it's a liquid, it's easy to ship, you can pump it out of the ground. Coal, you've got to go get it. You've got to dig it out, you've got to mine it, and it's not so easy to get. Natural gas. Where is natural gas? Russia. Again, we saw that in the news this past year, right? When they turned off the pipelines to Europe, they disrupted supplies over price negotiations. But Russia's got a lot of gas. Iran, Qatar, or Qatar, however you want to pronounce it, you can see those are the big three players in the world. You don't see the U.S. very much in there. There's this little orange sliver. Really, if we talk about basing our economy on natural gas, all we're replacing is one imported fossil fuel for another. Okay, so that's why when some plans out there are saying we've got to use natural gas as a replacement for oil, but you can see why that doesn't seem to make much sense actually in the long term. All right, so that's kind of my tutorial on what the problem is and where is the problem. So it's a national security issue, right, where our energy is. And I wanted to lay out a little chemistry. I am a chemical engineering professor, after all. And so why look at biomass? All right, well, here I put up chemical structures of coal, oil, and natural gas. So those are the three fossil fuels that we've mentioned. And so here is a structure of coal from the Proceedings of the National Academy. I just borrowed a structure from the journal. And it's just got a lot of carbon, and there's some hydrogen in there, and a few other atoms like nitrogen and oxygen. But in general, it's mostly carbon, and it's got some hydrogen in it. Oil is about one carbon with two hydrogens, just repeated over and over again. And natural gas is one carbon with four hydrogens. So what you see is why the properties of these materials are so different. Four hydrogens with a carbon, that's a gas. All right, two hydrogens with a carbon, that's a liquid. And almost no hydrogens with the carbons, that's a solid. And so it's that composition that changes the physical properties and how easy it is to process and how easy it is to get and move around. Now, what's biomass? Biomass, in general, is really about two hydrogens per carbon, which is similar to oil, but it's got an oxygen there for every carbon. Okay, that's the problem. All right, that's why biomass is not so effective to use for energy. You've got to get that oxygen out. All right, and so the main player in all this is if we can get the oxygen out, we have something that compositionally looks like oil. All right? So how is oil used? So what I'm really going to talk about in this discussion is looking at biomass, how to process biomass to replace the products from oil. I'm not going to talk about coal. Coal typically goes to electric power, right? We're going to make electrons or electricity for your homes. All right, natural gas is used to heat homes, it's used to make chemicals and other things, but not to fuel cars. But what is oil used for? In this nice graphic from the DOE, you can see the majority of oil is used for transportation fuel. So gasoline and diesel fuel with heating oil is over 60%. That 18% other products, those are chemicals. Okay, so the whole chemical industry, petrochemicals, you've heard that term before, is based on that less than 20% of the barrel of oil. Okay, the rest is going to asphalt and transportation fuels and other parts of the economy. Okay, so in my view and in many others, then what we're dealing with is biomass is a renewable carbon source. Okay, so it's growing and extracting carbon from the ground and from CO2 in the atmosphere. And so if we use it to convert it to a fuel and burn it, we're really not contributing substantially to carbon dioxide emissions if it's processed correctly. Okay, this is another life cycle analysis issue. If you're going to burn down all the forests in Brazil to plant energy crops, you've just released tons and tons of CO2. So that's what I'm not talking about, correct processing. Okay, that's not correct. So if processed correctly in a sustainable way, it is possible to minimize the carbon dioxide footprint. All right, and we think that the greatest potential for biomass is really in the transportation sector. Okay, so it's not to make electricity. All right, it's not to heat your homes, but it's for transportation fuels. And why is that? Well, electrons are great, okay, and many of you have probably read Friedman's book about clean electrons. But batteries have a lot of problems still. As you can see here with my little technology, this is probably a battery issue. Okay, battery storage it's too bulky right now. It's expensive. How do you put batteries to fly airplanes and large trucks? We are putting them in cars, but the mileage is limited. Fuel cells are often discussed as the solution to that, but right now almost every fuel cell that works in a mobile sector requires large amounts of platinum, which there is not enough platinum in the world to satisfy all of the fuel cell needs to displace internal combustion. But biofuels blend straight into our infrastructure. Okay, we don't have to really change anything because engines will burn biofuels as long as we make the fuel look like oil, which we can do through chemical engineering. All right, so what are the options for biofuels? One, ethanol, right? That's what everybody's heard about. And what is the next generation ethanol? It's not from corn. All right, I collaborate with a research center in Iowa, and so my collaborators in Iowa are still hardcore corn advocates, okay? But there's a lot of controversy about using corn for ethanol. But cellulose, and I'm going to talk about cellulose, what it is, in a few moments. But taking cellulose to ethanol, that is something that's being looked at as a reasonable option. So what I want to do in the remaining time is really explain these three options. These are what you're going to read about in the newspaper. This is what a lot of research in this country is going toward. Number two, biodiesel fuel. Let the plant make a lot of its own oils and then just do final conversions of those plant oils to fuel oils. And then finally, hydrocarbons, making actually directly gasoline, diesel fuel, or fuel alcohols directly from plants just by over-processing it, taking it apart, and reassembling it again. So those are really the three main options. Now, one major question that comes up all the time in the papers is there enough land mass to do this at all? And this one is not solved. Okay, there are a lot of people looking at this problem, and I'm not an agricultural expert. I just have to go with what the government tells us, right? And so this is just a quote from 2005 that says, well, a lot of people have looked at this and say, we think we can get about 1 billion tons from agriculture in this country, okay, without displacing food. All right, and so that's the issue. When we're talking about biomass, we don't want to displace food to grow energy crops. And so how much do we really have available? It's about 1 billion tons, and a lot of people think that that's reasonable. And that, if we can convert that effectively, is about 30% of the nation's transportation fuel supply. So we're not talking about replacing all of it, all right? It's just part of it. This is why right now, as far as we can tell, after looking at all of the energy issues, there is no single silver bullet solution for energy. So I'm really just talking about one part of one sector, which is transportation using biomass. All right, now, where do you grow the biomass? Here's a map of the United States, and it plotted on here are different types of crops that different regions might think about. And you see terms, I remember when in the George Bush era, he was talking about switchgrass in one of his, it might have been the State of the Union, I can't remember, but I think it was. But you can see another crop called miscanthus. Some people are looking at poplars, okay, wood. But there are a lot of crops that one can think about that grow rapidly and can be efficiently used to make fuels. And I just show this picture here to show how fast these grasses grow. So here is miscanthus. It's a grass I'd never really heard about since, as a chemical engineer, but a lot of people know about it. The Europeans are looking at it very closely. And also in the United States, you see here that this lady holding this pole shows that it's, 12, 15 feet in one growing season in Illinois. So it's a rapidly growing crop. But how do you get fuel out of that thing? Okay, it's not like corn, all right? Corn is a food. We can eat corn, and the fact that we can eat corn and turn it into energy in our bodies means it's easy. Okay, taking grasses to fuels is hard, all right? And that's why we can't eat grass. Okay, so what we have to do is we have to deconstruct that stuff, okay, to sugar. And then we do our old favorite, we've been doing for thousands of years, we ferment stuff and we make alcohol. Okay, we've done it not for fuels, but for other reasons for many, many years. But the key is we've got to get to sugars, okay? And we can do that from corn and other grains and fruits and so on. But to get it from grass, we have to tear apart the cell walls. And so here is essentially the main problem. The cell walls of these plants, as I show here on the right-hand side of this slide, are composed of these three components, one called lignin, one called hemicellulose, and the other called cellulose. And the cellulose is what we really want here, because cellulose is made up of glucose units. That's a fancy word for sugar. Okay? And if we can tear apart cellulose and get the sugar out of it, then that's what we ferment to alcohol. Lignin is like plastic. Okay? That's what gives the structural stability to the trees, the grasses, and plants. That's why they stand up and grow. And so it's hard stuff, and it's wrapped up in there in that cell wall, and you've got to get it out of the way. And hemicellulose is also made of sugars, but it's a different kind of sugar. It doesn't ferment as well. All right, so the key is tearing apart this stuff, and that's where the cost comes in. All right? This is just a cartoon showing that there's some pre-treatment that's needed to blast this stuff apart to get the cellulose out. Now, this is why we can't eat grass, right? Ruminants can do this. All right, cows and so on. Animals that have a rumen can eat stuff. It has the enzymes in their rumens to break down the grasses to get to the cellulose and the sugars. Okay, but humans can't. We don't have rumens, so we eat corns and stuff that has starches that break down to sugars and so on. That's where we get our energy. So this is the kind of analogy I want you to take away is this is why, the processing of biomass is difficult. Okay, it's the exact same reason we can't eat it. All right, so once we actually pre-treat this thing, then you have these cellulose chains that we have to break apart, and this is an enzyme that actually then takes the cellulose and decomposes it to sugar. And this is a cartoon showing how it takes the chain into its pocket in the enzyme and actually clips it apart into individual sugar units, and then those sugar units go on into our fermenters and stills, and we make alcohol, all right? So that part we know really well. So here's our overall plant and why it doesn't work so well economically. All right. One, at the very top, we have to harvest biomass. Okay, this is the other problem with biomass as an energy source is that it's wet. It comes along with a huge amount of water. And so a lot of life cycle analyses have been done that say you can't ship biomass very far, maybe 30 miles, maybe 100 miles, but it's not very far because otherwise you're spending too much energy moving around a bunch of water. Okay? So you've got to take the biomass and process it locally. So you talk about local farms and local produce. This has to be local as far as we can tell to make it pay off. All right, so once you have an area that you can process all the biomass locally, then you have these pre-treatment steps that are pretty costly and inefficient. And what are those steps? They're pretty harsh. There's ammonia treatments. There's sulfuric acid. That's a way to go. There's, heat a lot. Use steam and so on. So these are very costly things. Okay, and this is why it has not played out commercially. So everybody likes corn because it's easy. All right, we have corn in surplus, and it was subsidized by the government, and it's very easy to make sugar. But in the long term, it's probably not going to work, in my opinion. But this one, there are large groups in this country that think this is a way to go. But we have to overcome these pre-treatment issues, the local issue, and then the enzymes used to break down the cellulose. So those first three steps are the economic problems that we have to deal with. And the technology and the economics are hand in hand on this. And the last one we know really well. That's how to ferment it and make alcohol. Okay, so that's what it takes to make ethanol from grass. Okay, and we actually have students do that in their first year. We had a project in my department for engineers to come in and take lawn clippings and make ethanol. And it was pretty fun. They learned a lot about it. They made like a few drops. It was really not very much. And so they realized how hard it was to do this, okay, which I think is a great educational experience. Now, the next possible player in this is biodiesel. Okay, now here's some more chemistry for you. So for those of you that have had chemistry in the last few years, you may recognize some of this. If you haven't, you may recognize the word triglyceride. My doctor talks about that one. And in his mind, those are bad, right? But here they're good, okay? But triglyceride, it's the same compound that your doctor tells you to take down. And that's, in this case, that's what vegetable oil is. And so this is the structure of vegetable oil. It will burn, right? It's just not so effective to use as a fuel. And so it usually undergoes a little bit of processing in a reaction that we call transesterification with an alcohol. And I show on the slide methanol. And it makes the fuel. That's the biodiesel fuel that's in that green box up there. And that's what you see in the UVA transportation buses as burning a blend of biodiesel fuel with regular diesel. So it's not exactly the same as diesel fuel. It's slightly different chemically, but it burns pretty well. Okay? And then there's a byproduct, glycerol. And glycerol this is another problem. I have to step back and say that when you're dealing with energy, the numbers are so big, if you make any byproduct at all, the market for the byproduct could actually determine everything. And so glycerol was being made in huge amounts, and what do you do with it? You could only make so much soap with it, right? That's essentially what it used to go to, and some cosmetics and things. So there's a lot of research, including my own lab, is trying to figure out what to do with the side product of this. Do you make it into a fuel? Do you make it into a chemical? But the mismatch of scale for energy use and everything else is a big problem in the economics of these things. All right, biodiesel, that's an easy one to do. Okay, farmers do this one in their barn. We have high school kids doing this for science projects now. And so I just grabbed this one off the internet that shows you can press oil seeds, you get vegetable oil, or you can use used oil from fast food restaurants or other restaurants. And then you react it with an alcohol, you make some crude product, you can use water to wash it out, and then you end up with the phase separation. As we all know, oil and water don't mix. So the water separates from the oil, takes away the waste products, and then you have a purified product that can you put right into an engine. So that's how you make biodiesel in the old way and in the current way and most of the way in the United States. And this is a relatively new industry. You can see here in 2000 only 2 million gallons were made. Okay, but over 700 million gallons were made by 2008 in this country. So that sounds like a big number, right? 700 million gallons. But I got to keep reminding you the scale of what we're talking about is everything in dealing with energy. And so 700 million gallons, how does that compare with what we actually use in this country? Well, we use 40 billion gallons of diesel fuel per year. Okay, we're less than 1/40th of the diesel fuel usage in the United States already at 2008 production for biodiesel from vegetable oils. And as you can see on this map, those plants are spread out all over the place, okay? And it has to be, right, because of the economics of biodiesel. Now, biodiesel is a little different because you can ship vegetable oil all over the place. As long as somebody presses it out or they ship the seeds and not the whole plants, the economics of shipping it are a little bit different. So you can locate things on coastlines and near transportation routes. But my understanding is that there's not enough vegetable oil in this country to really make a significant dent in the diesel needs. So why ever do this, right? Is this just a waste of time? But I do want to tell you that the EPA has legislated clean fuels, right? So the fuels that you're burning in these trucks as you see out on the highways right now is a lot cleaner than it used to be. It may not look like it, but it is. There's a lot less sulfur. And when you remove sulfur from diesel fuel, it doesn't lubricate as well anymore. And so by purifying the diesel fuel, you change the properties of it, and you have to add something back to restore its properties. And only adding 1 or 2% of biodiesel actually restores the lubricating properties of the dirty petroleum diesel fuel. So now you can see that there's always a need for even small amounts of a renewable fuel additive. So there is a market there. Okay, it's not a large one, but there is a market for it. All right, what's the player here? As I already mentioned, that feedstock is the big problem, right? Biodiesel economics really rely on the feedstock. Vegetable oil is expensive, okay? And there's not much of it. We've looked at soybean oil here, right, in this country mostly. People talk about sunflower and canola or rapeseed oil, and a lot of other countries are looking at palm oil. But when I was in China for a government panel, we came across an English translation of a newspaper that they were planning on planting a substantial acreage, almost the size of the United Kingdom, in Jatropha, okay, to make biodiesel fuel. And I scratched my head on that. I didn't really know too much about it, but it's a plant that grows in horrible soils, you know, on the sides of railroad tracks. It doesn't really compete with food. And so India and China are investing more in this plant, Jatropha, as a seed oil for biodiesel fuel. Now, will it matter? I don't know. Remember, the scales are not so great when you're dealing with seeds. Okay? So one future source that's really getting a lot of play right now and a lot of study is algae. Okay? That is a completely different scale. And the scale is shown here. This is a calculation done by the National Renewable Energy Research Lab, Air Force Office of Scientific Research workshop, there was a presentation by Benjamin, and there are various numbers by other folks that report similar types of things, but I just chose these numbers to illustrate. Look at how many barrels you can get per hectare per year from soybeans and sunflower and canola. Not very many. But algae, an order of magnitude higher than palm oil and more than that from these other seed oils. So now you start thinking, well, maybe there is a resource that can produce enough of an oil that might have an impact. Okay? And that's the one that we're looking at also in my lab and a few universities around the Commonwealth. Here's just a picture of the algae farm from the Virginia Coastal Energy Research Consortium. It's southeast of Richmond. But there are some real problems here. Okay? Problems, one, it takes a lot of nutrients to grow algae, lots of water, and lots of light. Okay, so there's a lot of engineering involved in this. And there's a lot of synthetic biology, people making new organisms to make lots and lots of oil. But anytime you see these, look at open aquacultures like this, large farms of algae, the native strains always win. Anytime you put in something that you genetically engineer, it's just going to get taken over by what just lives in the environment in that area. It happens every time. All the people I've talked to, they can't solve this problem. Right now, algae, you have to take it out, dry it, squeeze out the oil, and then process it. Okay? Very costly. All right? So synthetic biology folks, they're trying to create algae to kind of spit out the oil, secrete it right out, because if it does, the oil floats to the top and you skim it right off. And that's kind of cool, right? But the key is, can you keep the algae that you may specially engineer alive and not losing out to the native strains? Okay, things that are going to grow naturally and take it over. So you've got this biology that you're fighting, this ecology. All right, so some of those are the challenges that we're dealing with. Now, ExxonMobil, this is the one they're betting on. So this summer, they announced a $600 million investment in algae. So I talked with their head of research recently. We had him for a seminar in our department. And they said, yeah, they took their best scientists and looked at all the biomass issues. And they said, well, we found so many problems with scale-up in the cellulosics and others. But they said, this one we think has a possibility of scaling. Now, that's all I know from what they've reported publicly. But it's some real dollars going into it. All right, and my lab is working on some new catalysts to do that transesterification, to take those triglycerides to make fuel oils. And we're trying to work on solid materials now to do those reactions so that we get highly purified byproducts. So I don't really want to spend much time on this slide, just to let you know that, yeah, this is an aspect of some research that's going on here at UVA. All right, the last issue that I want to talk about is just tear apart the biomass and rebuild it. Okay, that's kind of the grossest way to do it, and maybe the easiest. And there are some companies that think this is the way to go. So here is a joint venture with UOP and Ensign that they've come up with the production of pyrolysis oil, where you just heat it up. You just take anything, trash, biomass, you heat it up high enough, and you decompose it, and some of the oxygen comes out as water, most likely. Stuff decomposes, and you're left with this black, oily stuff. And so it looks like oil, doesn't it? It's pyrolysis oil. It's not oil. It's got a lot of other stuff in it. But it's processable. And so that's what they're betting on. You can take hardwoods and softwoods and barks and fibers and bagasse and, waste paper, feed it into this stuff, and get this kind of oil out. All right? That's kind of an interesting way to go. All right? But what it does is it creates a liquid product. You can ship it around. The idea is couple to a refinery, send it to a refinery by a major oil company, and just throw it right in their oil stream and process it like a normal oil with some minor adjustments to the refinery. And so that's a kind of an interesting way to go. Okay, it appears to be scalable. Okay, it probably takes a lot of energy, right? You're heating this stuff up to decompose it. And so the economics still have to be worked out. Problem is, these oils contain a lot of other things that you really don't want in there. They're corrosive, they've got a lot of acids in them, and so there are a lot of handling issues involved with it. The oil is not stable. Okay, it's not like oil you pump out of the ground, which has been there a long time, right? You've just created this unstable, highly acidic, probably pretty toxic material. All right. So, again, the transportation is an issue. if you're taking a bunch of leftover agriculture, you have to do everything locally, and so you can't have this big refinery, on the coast of Texas or the coast of Virginia and ship all of your biomass there. You have to do it locally. So there are some companies, and I just picked these two off the internet because they have nice pictures, of mobile units where you can feed your biomass locally. Remember, there's that certain zone of 30 to 100 miles or something that depends on the economics of where you have to process this. So the idea is you process it locally and ship off your oil to a refinery or to a central processing facility. It's an interesting idea. It's one you'll hear about. It's one that's being looked at pretty seriously in this country and in Europe. In fact, in Finland, which is dependent mostly on forest products, they have this as part of their one of their refineries over there. And the final option that I want to mention before I have to stop is the total deconstruction and rebuilding. Okay, you can take animal waste, corn waste, wood, sawdust, trash, anything, and just gasify it. Okay, and remember the stoichiometry of biomass was CH2O. Well, what comes out, you make CO and hydrogen gas. Okay, if you gasify it, and you take that and just rebuild it into oil, according to a process that we've known for a long time. It was invented in Germany in the 20s and commercialized in the 20s and 30s. And that process is named for these two folks here, Fischer-Tropsch. And this makes a very clean diesel fuel. Okay, it has very little impurities because you've cleaned up the CO and the hydrogen after you've gasified the biomass. And so you're essentially just growing the chains on a catalyst, and then you make your fuel after you just gasify everything that you've had. All right, now, do we do this? Absolutely we do this. We do this one on a large scale in this world. Sasol is in South Africa, and this is essentially a company that kept that country running during apartheid when the world had an embargo against South Africa. So their economy developed around synthetic fuels. Okay, so they had coal, and they could convert coal to liquid fuel by gasifying the coal and then creating liquid transportation fuels. So it's the largest producer of synthetic fuels in the world, and right now 25% of South African fuel is derived from coal. And so if you think about it, if you can do it with coal, you can easily do this with biomass, right? You can just gasify the biomass and then rebuild it according to this method. And I just, when I was in South Africa, we had a collaborative project in the early part of this decade. I was struck by the fact that when I turned over a 50 Rand banknote, there on their banknote is Sasolburg that essentially shows the reactors that make the synfuels. And so it was so important to South Africa, it shows up on their money. So as you can see, these very, very large-scale reactors to make synthetic fuel. So are there challenges? Absolutely. These things are really large-scale processes, and my understanding from the engineering is that they pay off at the large scale only. And so biomass is small scale. Remember, it's local. If you have to do this stuff distributed, everything has to be small scale. So this is a whole different problem. This is the scale-down problem. And so can you do gasification and then reconstruction by Fischer-Tropsch at small scale? That, we don't know. That's a serious engineering issue, and that's what we're working on. So, again, a couple problems are listed here, and it always comes down to economics. All of these. These are known technologies. These are things out there that scientists and engineers have come up with, but right now don't play out economically. Okay? So where do I think we stand on all this? This is my last slide, so we have some time for questions. Is that there are a lot of routes. We can take biomass and make a lot of different things from it. All right, we can make fuel alcohols, we can make biodiesel fuel, we can make synthetic fuels by just tearing it apart and rebuilding it. Okay, and there are significant challenges associated with all of them. And this is why I think we have a problem, because we can't identify which is the best one right now. How in the world do the scientists and engineers help set policy when we really don't know the right answer? I don't know the right answer, and as far as I can tell, no one knows the right answer right now. So there's no easy policy decision in this one, because as you can see, there's still a lot of research that needs to be done. And right now, these things are not yet cost effective. If we knew what the winner was, then we could probably have policy decisions that allowed subsidy to let the infrastructure to build up. But right now, I don't know what the winner is. But I just hope that what you took away from this is you learned a little bit about what the issues are, how you can take biomass and create liquid fuels, and that it probably will be a player in the near future because this is something we can do pretty soon. Okay. So thank you very much for coming and listening on a Saturday, and hope you enjoy the game today. Go Who's!